Hi, folks. I want to spend just a few minutes today talking about two ways that systems can grow or change. They're called linear and exponential growth. So, linear growth, I'm going to show it to you through this graph here. Linear growth means that you have a constant speed. So, in this graph, I want you to imagine that you've accepted a job where you get paid $1 million every year. It's a pretty good deal, right? So, after the first year, you get 1 million. After the second year, you're up to 2 million. That's 1 million more. On the third year, you have 3 million. That's 1 million more. And this graph is showing those points increasing. So that's 3 million and then 2 million. It's counting up the total amount of money that you've got. So that can get pretty big. After 30 years, that's $30 million. That's an amazing salary to get. And if you imagine your career is like 30 to 40 or maybe 50 years, that's 40 to $50 million. That's pretty good, right? Good deal. So linear growth is steady, it's constant, it's reliable. So examples of things that undergo linear growth are a car that's going at a constant speed, walking at a constant speed, getting paid a steady wage. Like the word steady and constant is in there. It means that it changes by the same amount every single time. Okay, I'm going to contrast that with a different kind of growth where the speed changes, where it gets faster with time. So let's imagine a ridiculous scenario where you agree to accept a salary of $1 per year for the first year, but then $2 a year for the second year, and then 4 for the following year. So it doubles your new salary each year. Obviously, that's a worse deal than $1 million a year, right? So on this graph with this scale, let me just show you a couple years worth. I've got the green one, which was the $1 million per year, and this purple one that you can see right there that's stuck down at zero that doesn't seem to be growing, but actually it is growing. So after 1 year, it's $1, and after 2 years, it's $3 total. So 1 for the first year and 2 for the second. So it's not the same amount each year. And then on the third year, you're up to $7 million because you increase by 4 the next time. So each year, the amount that you get doubles. So let me show it after 10. On the original plan, you're up at $10 million. And after 10 whole years on the second plan, you're only up at $1,024 because you grew by $512 in the next year. So it is increasing, but it's still not enough. And it's nowhere near as much as that $1 million per year. So on this graph of this scale, you basically can't even see it move. Okay, so my question for you to consider is there a point in the future where you would rather switch to this purple plan instead? So I want you to pause the video right now, write down what you think. Will it ever be better to switch over to the doubling plan? That would mean that at that point, you'd be getting more than $1 million more per year. So pause right here. Tell me what you think. Okay. So what do you think? Do you think it's going to be after 20 years? Is it going to be after 50 years? Is it going to take 1,000 years for it to catch up? Okay. And then I have kind of a follow-up question to that. Will it ever be better to have been on this doubling plan the whole time? Because even when we get up to $1 million per year on this purple plan, the green one has already been getting $1 million per year every year. So it's going to be way ahead. That purple plan is going to have to catch up by more than $1 million per year in order to ever actually get there. Okay, so let's keep going. We're going to increase the number of years, and we're going to go up to 20, and we finally start to see some movement in this purple one. So the green one is still increasing by 1 million each year, and the purple one finally budges off that bottom line. Down there, it's at 26,000 total after 17 years, 52,000 after 18 years, after 19 years, sorry. And then after 20 years, it's finally up to 1 million total after 20 years, where the other plan is at 20 million. But notice something interesting. In this very next year, between 20 and 21, you go from 1 million up to 2.09 million. So it's actually grown by more than 1 million in year 21, where the green one only still, because it's a constant speed, only grew by 1 million more. So actually at this point right here, that purple one's growing by more each year. So maybe year 20 to 21 is the right time to flip over because it's going to start giving you more each year. Less total, but more each year. Okay, now let's just keep going. I mean, obviously it's going to take another 20 or 50 or 100 years before it catches up, right? But this is the crazy thing about this. So in the next year, we're going to go from 2 million to 4 million. Oops, hard to control that. Let me just type it. So in 23 years, we're at 8 million total. In 24 years, we're at 16 million something total. And see how it's growing by way more than that green line is? After 25 years, it shoots right on by. So between year 24 and year 25, you actually would say, it would have been better for me to be on that doubling plan the whole time because it ended up much higher. And it's not going to slow down. It's just going to keep getting bigger by more and more each year to the point where I now have to zoom out to be able to see that purple one. It's huge now. Okay, so we're going to stop there with this little graph, and I want to think about, are there any real situations that are like that, that grow like that, where we have this steady constant growth versus this not steady? It increases how quickly it's changing, but eventually it just sort of, it almost explodes. Do we know any systems that are like that? Well, one example that we're talking about right now in the class, and we'll continue to talk about, is a nuclear chain reaction. In a nuclear chain reaction, when one uranium atom gets split, it releases 2 or 3 new neutrons. And those 2 or 3 new neutrons then go on to hit 2 or 3 more uranium atoms, which then themselves split and release each 2 or 3 more neutrons. So you're going to get 2 or 3, and then between 4 and 9 more, and then between 8 and 27 more. It's just going to keep growing and growing and growing. And that's how you get one of the ways you get the enormous amount of energy out of nuclear reactions. So we're going to use this idea as we look at different energy technologies. Is this a technology that has exponential growth in it, like nuclear energy? Or is it one that only has linear growth in it? And then we're going to compare it to the needs of the population as well, asking if the need or demand has exponential growth in it, the way that populations can grow exponentially, or just linear. So I'm going to stop there and ask you to look for more examples of technologies that have linear growth in them, constant speeds, constant rates of change, versus exponential rates of change, where it keeps increasing how quickly it changes.